Hi, this is Professor Fernandez, and this is video 2 in lesson 8. We're talking here about the limit definition of the derivative. So we'll do a couple examples here from Calculus Simplified to see if we can get more comfortable with this concept. You'll notice over here on the lower right, I have inserted that limit definition of the derivative. So let me just zoom in there, go over it for a minute. So suppose we have a function. The definition of the derivative of the function at a particular x value, we are denoting that f prime of a is defined by this thing down here. Okay, so I want to break down what is going on. So first of all, notice that this part here is the thing we're taking the limit of. Okay, this is sometimes called the difference quotient. It is a quotient, and in the numerator we have a difference, so that kind of explains that nomenclature. So what's happening in the numerator? So we have the difference of two function values. The first function value is f of a, so that's over here. And the second function value is f of a plus delta x. So long story short, we're looking at the change in y values. That's the numerator. Between x equals a and x equals a plus a little bit more. That's the delta x. And then in the denominator, we're taking that same change in x values, delta x, and we are dividing by that. So that's the first thing to realize, that this difference quotient, although it looks kind of complicated and convoluted, this is just change in y over change in x. On the graph, this would be the equivalent if we draw here what's going on. If this is the x-axis and this is x equals a, and then this is a plus delta x, you know this little part here is delta x. And then let's say the function looks like this. Okay, this over here, the y value would be f of a. And this over here, this y value would be f of a plus delta x. Okay, so then what's really happening? Well, I guess I should move things here so it looks a bit more like where the points actually are. There we go. So then what is this difference quotient? Well, the change in y is exactly f of a plus delta x minus f of a. That's the numerator. Okay, and then the change in x is over here, right? A plus delta x minus a leaves you with delta x, which is what is down here. So this really is the change in y over change in x. Graphically, it is the slope of what's called the secant line, okay? The line connecting these 2 points. Okay, so this is a difference quotient. It's just a slope, change in y over change in x, between these 2 points, this one and that one. All right, and then so what's happening for the rest of this limit definition of the derivative? We are taking the limit as delta x approaches 0. So both in the interactive figure that's referenced in Calculus Simplified, and then all over the web. You know, if you search something like tangent line interactive applet or something, you will find an animation of what happens if I take this delta x and I make it smaller. And you can just see here that what's going to happen is this distance gets smaller. So this second point right there is going to move a little bit further down the graph, maybe there, right? That would correspond to a smaller delta x, and then maybe an even smaller delta x, and even smaller. So then what happens is that originally, if your points look like this, and here's your secant line, then the next point looks like this, and then there's your secant line. And then the third point looks like this, and then there's your secant line. You can see that the secant line is converging to what we would call a tangent line. In other words, if this is the graph of the function, the one that we've been working with here, and this is the f of a comma f of a point, then the tangent line would be the line that just touches the graph, okay, at that point. The graph may kind of curve over elsewhere, so the tangent line actually may intersect the graph somewhere else. But if I were to zoom in here and just look at what's happening for this part of the graph, right, then I would see a line that touches the graph at just that one point. So long story short, by taking this limit, which is the last ingredient in this definition, we are in fact taking the difference quotient, the slope of that secant line, and we are shrinking the change in x to 0 and approaching this tangent line. So in other words, we're still finding the slope of a line, very special line called a tangent line. And the notation here is f prime of a. So One thing to remember from this, very important, and this is something that will recur over and over in calculus, f prime of a, which is the notation for the derivative, is at its most fundamental core a slope. A slope of what? A slope of a tangent line, okay? And then the notation again is f prime of a. All right, so after that review, let's go over here and calculate f prime of 1 for this function, f of x equals x squared. And now we know a lot, right, about what we're doing, how to do it, and what we're going to get. So first thing I'll do is I'll set up the difference quotient. Notice that I'm asked for f prime of 1. In the definition, right, if I go back here, f prime of a, well, in this case, where f prime of 1 is what we're calculating, a is 1. So I'm going to put 1 in here and 1 in here. All right, so the difference quotient is f of 1 plus delta x minus f of 1 divided by delta x. And then at this point, I use my specific function. So f of x equals x squared. So I'll do the easiest part of the numerator first. That's this part, f of 1. I put in 1 for x, I just get 1 squared. Great. Then the other part, which is less easy but not so bad, I'm going to put in 1 plus x for x. So the function just squares that 1 plus x, the entire thing. And then the denominator stays delta x. Great, so now I'm going to simplify. In the numerator, I'm going to square this out. Remember that a plus b squared, the quick way to square this is to remember this formula. So I'm going to apply that here. So 1 squared plus 2 times 1 times delta x plus delta x squared, right? So 1 squared, and then here's that term, and then here's that term. Okay, and then I'll bring over this minus 1, all divided by delta x, all right? And now certain things cancel. 1 minus 1, that cancels. And then I'm left with 2 delta x plus delta x squared in the numerator, divided by delta x. And at this point, I can factor from the numerator a delta x. So I'm left with 2 plus delta x divided by delta x. And as we've said before in previous videos in this series, I am going to be calculating a limit. There it is down there. So I'm just going to cancel out these delta x's. And I'm going to write equals 2 plus delta x, right? Understanding that this equality is only true when delta x is not equal to 0, which is indeed what's happening because remember the limit approaches indefinitely, never arrives, right? So we're approaching 0. We are not setting delta x equal to 0. Okay, so if I zoom out a little bit, I now have my difference quotient calculated. It is this. So f prime of 1 is going to be the limit as delta x goes to 0 of the difference quotient that I simplified, which is 2 plus delta x. Okay. What's nice about this is that there's only one place where delta x appears, right? There it is. So as we've done before, we could use the limit laws. The limit as delta x goes to 0 of 2 is just 2. There is no delta x. The limit as delta x goes to 0 of delta x is 0, right? Delta x is going to 0. There's a delta x. 2 plus 0 is 2. So that is my f prime of 1. Awesome. So recap of the steps involved. Number 1, calculate the difference quotient. Okay, that gets us over here on the right. Number 2, calculate the limit of your difference quotient. And then number 3, simplify whatever arithmetic you might have to do, and that gets you to f prime of a. Remember all the work we did at the beginning of the video? We now know exactly what this means. This means that if I were to graph the function, in this case x squared, there's y equals x squared, and go to this x value, x equals 1, where I know that y is 1 because 1 squared is 1. Then the fact that f prime of 1 equals 2 tells me that if I draw the tangent line, right, this is the tangent line there. Remember, it just touches that point and nothing else in a very zoomed in local manner. Then I can say that the slope of this line is the derivative value, 2. Okay, so that gives you a sense for what the derivative information gives you, what it means, the slope, how do you calculate it, and things like that. Okay, so then now let's move on to the last example here. Remove some of the clutter. This example says, find the equation of the tangent line, there it is, at the point 1, 1 on the graph of x squared. All right, so we've already done most of the work. This is a different type of problem, right? We are not asked to calculate, we're asked to find the equation of the tangent line. How do we do this? Well, let's use some logical reasoning here. We're supposed to find an equation of a tangent line. Okay, a tangent line is a line. So remember our different ways, different equations, different formulas for finding the equations of lines. We need to look at what information we're given. We're given the point, and we're given that it's on this graph. Okay, so now is where we use the other part. It is a tangent line. What does that mean? That means that its slope is the derivative. In this case, we're looking at the point 1, 1. In other words, x is 1. So the slope is the derivative f prime of 1, which we just calculated to be 2, right? Because the function we're using here is the same one we were using in the example above. Okay, so now let's redo our analysis. I'm asked to find the equation of a line which has slope 2 and passes through the point 1, 1. Aha, so I have the slope and the point, so I'm going to use the point slope formula for the equation of a line. Excellent. So what is the y value of the point? 1. What is the slope? 2. And then what is the x value of the point? 1. There it is. That's my equation of the tangent line. It's not simplified, so I could certainly do that. I would add 1, distribute the 2, and then simplify that way, so 2x minus 1. So now, if I were to go back and draw the picture all over again of my y equals x squared graph that passes through 1, 1, now not only do I know that the slope of this tangent line is 2, I also know that the equation is the thing we just calculated, 2x minus 1. You can certainly play around with this and say all sorts of things. For example, it is a tangent line. It should pass through this point, right? We always say tangent lines touch the point of tangency. Indeed, when x equals 1, y would be 2 times 1 minus 1. That's 2 minus 1. That's 1. So when x is 1, y is 1, this tangent line indeed passes through the point 1, 1. That's the point of tangency. Okay, so I'll zoom out and then do a very quick little recap. If you want to calculate the derivative for a function using the limit definition, later on in this course, we'll find faster ways than doing all of this. But if you want to calculate using f prime of a using the limit definition, right, that's what was down here. You would like to, first of all, step 1, find out the difference quotient. Step 2, take the limit. Step 3, do the arithmetic. That is f prime of a. What does f prime of a tell you? It tells you the slope of the line tangent to the graph f of x at x equals a, the slope, okay? And then if you want, you can later on figure out the equation of the tangent line. How do you do that? Well, you have the slope. You have the point of tangency, right? You needed that to calculate the derivative. And then you use a point slope form. And then simplify, and you'll get your equation of your tangent line.